Hi, my name is Siegelmann. I direct the Binds Lab, and I would like to present a bit what we're doing. So in general, what we do in the Binds Lab is we looking at AI and we're looking at neuroscience. We try to find the relationship between them. Indeed, AI started with looking at neuroscience, and we repeat this process. Today, there are many groups that are looking either at one of them. We find that by looking at both, we can still ask bravely, what are current limitations of AI? Can we go back to neuroscience, find ideas? By doing that, I would like to show you some examples. So the first limitation of AI today, I think, is that AI is frozen after it's programmed or trained. So if you talk about AIs from the 80s, rule-based systems, it's all written if then else, and everything had to be processed in advance. The other option that is working today is neural networks that are shown examples, but the examples that are shown are through a training set that gives all the possible input outputs that somebody prepared in advance. So what happened is that the neural network load this data, and that's it. From then on, it's frozen just like the previous AI. So in reality, once we prepare AI, either way, AI or machine learning, it's frozen after preparation. And the similarity will be, if you want to think about animals that got through genetics information, and after that are not able to learn. So as they go, as they have things that they are doing, they cannot learn from their experience. That's kind of where I today. And the issue is that without this capability of lifelong learning, like animals, there are malfunctions and there is a lack of reliability, because if you are in new circumstances that were not thought before, then it's not working. So if you want to look at this little figure, time is on the x-axis and performance on the y. So during training, performance goes up and then it stays still. In fact, if you had a system that could learn from the experience, like a car, then the car will drive better and better, let's say on snow. But if you cannot open to experience, it can never get better. And in reality, if you get to things that it doesn't know what to do, it fails. What we want to have is that type of AI that continue learning with this experience, so it becomes better than in the end of the training set. And also, when it sees that things are not there, it opens itself. So that's kind of lifelong learning. And I was recently in DARPA, and I founded and managed this lifelong learning machine. And the idea was that I describe or define different pillars that will bring to lifelong learning. And many groups join us. It actually was a very large program, and work together on these different pillars to create this vision of lifelong learning. What I will show here from the lab is just talking about class incremental continuous learning and generalization, just two of the pillars. And the importance in lifelong learning is that we see new behavior at the end. So it's not just the system learned, but it actually use it in order to provide new behavior. So let me start with the first one. The first one is the continual learning and class incremental learning. So if you look at the left here and the bottom left, we see that there are many methods that were suggested for what is called continual learning or task continual learning. So for example, if you have many letters, one task will be to separate between 0 and 1. Another task will be to separate between 4 and 5. And all these methods can do that. They learn every time one task. And when you come to it with a question, you have to tell it which task it is so that they know to separate. So in fact, they're so good in separating 4 and 5 and 0 from 1 that it can never separate 1 from 4 or 0 to 5, because this is outside of what it learned. It's not a task. So this is not a very nice thing. If it was a person, you'll say that the person is an idiot. In lifelong learning, if you learn to separate 0, 1, and then 4 and 5, we want it to be able to separate all the other options, because that's what you do when you learn from your experience. So recently we suggested one way to try to do that. And this is by brain-inspired replay. It's a joint work together with Guido and Andreas from Baylor School of Medicine. So in general, if we learn something and we're now ready to learn another task, and we don't want to forget the previous task, one way to do is to keep everything that we learned in the past, and every time that we want to learn a new thing, so that the new thing will not create catastrophically forgetting for the old, we'll bring also the old and retrain it. So this idea of retraining was there in AI, but it's a very expensive and unscalable idea. It's also very not biological. You cannot just say, you know, oh, I forgot what I saw in Italy last year. Let me be there again so that I can see it. So we don't have that capability. So what we have capability is we cannot do retrain, but we can do replay, which means that we cannot really take the set as it was there, but we can generate. So if we generate things and bring them back, maybe that will allow us to learn a new task and remember the old task. But this is also not working very well. There are many papers tried to do that, not that successfully. So what we decided to do is to go to more details and to have brain-like generation. So the idea is that once we generate, just like in the hippocampus, we'll not generate all the way to the output. We'll just generate to some level of abstraction. And you can think about it as what happens in dream. You don't generate what you saw exactly perfectly. You don't have in your dream perfect input, but you have some thing that is like. So this is some level of abstraction. And interestingly, once we do that, first, it's very fast. We don't have to have very good like input data, but once we do that, learn just a little bit and then retrain, we actually get what we wanted, which is not just the task incremental learning, but the clustering and the classes incremental learning. So as we see here, we go through abstraction, and that kind of brings us to another idea, which is how we can do abstraction. You know, in general, abstraction is very important in AI and also to human, because if I saw a few examples and I can abstract them, I don't need to see these examples again. I already understood the idea. I can apply it to another things. I can do analogs, and really kind of smart way of learning is because of abstraction. So the question that we came, this is only at the Baines Lab, Patrick postdoc, Nick and Javier were two grad students. So the question is, how does the brain, the human brain, do abstraction? So what we notice is that if you look at the connectome, which is the way that the brain is connected through pathway and through measurements of MRI, if we look at the connectome, there is something very interesting. Actually, the connectome enables this abstraction. And I'll tell you very shortly how. So let's say that you look at the visual cortex, which is here, and you activate it. And after a short time, you see where the activation is in the brain, where it propagated next, where it propagated next, where it propagated next. And you can look like that until it kind of going around in the brain. And the one that is outside, let's call it visual being 1. And then we go to visual being 2 and 3 and 4. And let's say that we take the whole continuum and we cut it to 10 times, so that we'll have 10 beams, which tell us how far we are from the visual cortex. The same we can do for the somatosensory cortex, to the olfactory, to the smelling. So we can do olfactory, we can go like that, and we can summarize and average them all. And in that we take the whole brain and we put it in bins, which bin number 1 is the closest to the outside, and bin number 10 will be the deeper that we can. And the question comes, if we have particular tasks to do, which is related to abstraction and to different way of thinking, where will this fall? Will they all fall if they're very basic and they're just about like finger tapping, will they all fall in being 1? Or if it's very abstract, like thinking about democracy and love and fairness, will that fall in being 10, in the deepest? And the question is, how can we look where it falls? And for that, we take functional MRI. In functional MRI, we see the hemodynamic. We see where the blood is moving around in the brain. And we can correlate where the blood is moving to activity of neuron, because blood brings sugar and oxygen, which is what is used for neurons to fire. So when there is brain activity, they immediately calls on for more blood. So we can look at the fMRI. We look at 25 years of information of people that were asked to do a lot of activities in many countries, lots of experiences, and we look where they fall. And we realize first that when we do different tasks, they never fall in one bin. They actually fall in all the different bins. But what is interesting, they fall in all the different bins in different ratios. So what we did is we look for every experiment. Let's say the experiment was to memorize something. And we look, let's say, at 1,000 cases, 1,000 times that people did experiments like that. We took all the activity and we treat it like data science. So now we said, okay, let's look where the activities are more or less, and we draw a line, we look at the slope, and if the slope is negative, it means that most activity was outside in early bins, and if the slope is positive, it means that most activities were done deep inside, and we take all the activities that we see all the behaviors that we see, and we put them by slope, starting with tapping and going all the way up to naming. And you can kind of already see that these kind of behaviors become harder, more and more aggregated. Then we did another task to ask people to explain to us what is more abstract with what. And voila, what we realize is that the brain connectome is actually allowing us to have this kind of hierarchy, which is related to abstraction. So when we want to do high abstraction, it's very deep in. So this is an interesting idea by itself, but recently, just last year, student Alex Game from Binds managed to demonstrate that we can actually use it for very important problem of neural networks. So this important problem is we can take a neural network and train it on some training set, but how do we know if this is a good neural network to generalize beyond the training set, to test set, to other things that we'll see? So given, let's say, 10 different networks, which is good one for this task, which will be good to generalize? So what he noticed is that the same thing that happened in the brain happened also in deep networks. So if you look at more complex input, maybe like this 8, then the activity in a well-trained network is in the deeper layers. And if we start with more simple input, then the activities are early on. And we can see the slope for 1 is very negative, the slope for 8 is very positive. And the reality is that networks that have this high correlation between the complexity of the abstractness of the input and between the higher slope will be the ones that generalize very well. We compare to all other methods that try to find how well we generalize on numerous data sets and numerous options, and we find very clearly that our methods that we called CNA for cognitive neural activation metrics is interestingly finding the best prediction for every neural network, how well it will do on generalization, which is a very good and applied problem that was very needed. There is another key limitation, and this is about robustness. So if you see this student is from Georgia Tech, he's a friend of us, and all his life he wanted to look like Brad Pitt. So we gave him these glasses and voila, the system say Brad Pitt. And then, you know, you go around in your car, speed limit is 15, and you really don't want to drive so slowly. But if we just add this little part here, the speed limit is 65, you can drive faster. And what about stop sign? You see, the system doesn't really recognize this stop sign there. It says that there are people there. Other people there? Actually, it seems that the network was right. So there are differences between networks and between humans. We see things differently. And in reality, it's this extra sensitivity to patterns that make AI stronger and make AI not robust. So in DARPA, I also introduced another program, which was called GUARD, for guaranteeing AI robustness against deception. And after that one, I introduced two other, which is RED for the engineering of deception and reverse engineering of deception and secured training. But what is important here that there's no one answer. There is not one answer for whether something is strong or weak. The one answer is it is strong under some situation. And that's why we build there a test bed, which will say that my thing is robust if it's 10 hours outside and you have this and these computers. And under this, we can say things. I want to give you just a little bit of the taste. The first taste is that people who suggested explainable AI as a way to make AI safer, actually realize that it's very wrong. It's very easy to give you what you told us, how to explain things to you. It's very easy to trick the explanation. So if I have to separate between safe time and non-safe time, and I tell you now it's non-safe time because 1, 2, 3, 4, but this 1, 2, 3, 4 are not there. Another thing is that we cannot only rely on computed confidence, because it's very easy also to trick confidence. So it takes much more to get into robust AI, which is one of the things that we also work in the Binds Lab. In general, if you think that one person want to have, a prosthesis, you want this prosthesis to be trained in the factory, but not fully trained because you want it to be trained to yourself. You want it to generalize because you walked in one room. Now you're in another room. It's not exactly the same, but it's similar. You want it to be robust that other people cannot trick and get into that and cause you to jump from the window. So in general, there is hypothesis that perhaps in a few years, what we consider non-neural networks, which is this pattern classifier, perhaps will not be considered really AI if you don't have lifelong learning and generalization and robustness. So these are something that the Binds Lab is working on. In addition, we ask for what other important things that we have to put to AI. Humans, our character is so much our memory. So whatever we remember, who we are, what things happen to us, is doing the kind of giving us who we are. And can't we give memory like this to AI, that the AI will know who they are, will start having their own ethics, their own favorite things. Another issue is the partnership between computers and humans. It's beyond explanation and beyond ease of communication and beyond trust. How would you like to communicate with your friend? Why wouldn't you communicate like that with your AI? Then we care a lot about computational capabilities of natural systems and how we can take ideas from it for AI that will have better capabilities than today. And we also have been working for the last 5 years on ethics and morality. So if you want to hear more about Binds, please come over and we'll tell you everything. Thank you very much. Bye-bye.